Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional unceded lands of the Lekwungen peoples. Currently, in low Earth orbit, there is a very serious situation that, if left unchecked, threatens to spiral out of control and could have drastic consequences, not just for space exploration, for satellites, and humanity's presence in orbit, but also for life down here on the ground. I'm referring, of course, to space debris, also referred to as space junk, or orbital debris/junk. And there's a rich history behind its generation. Now, first of all, space junk is a general term, which is used to refer to every bit of debris and non-functioning piece of equipment that is currently floating around in Earth's orbit. This includes now defunct satellites, but also spent rocket stages, as well as fragments of spacecraft, satellites, and other missions that have been launched since the beginning of the space age. While much of this would eventually fall into Earth's atmosphere and burn up, or land in the South Pacific Ocean, an area known as the spacecraft graveyard, there remains a large and growing patch of junk up in space, which in many ways resembles the Great Pacific Garbage Patch. Whereas humanity's tendency to produce waste and microplastics that then find their way into the ocean is creating a growing problem for marine life, maritime travel, and the health of the planet in general, the growing problem of space debris reflects a growing use of space by national governments and private corporations, and the impact it's likely to have on the future of spaceflight, as well as life here on Earth. As mentioned, a considerable amount of orbital debris finds its way back to Earth. Not all of it lands in the South Pacific. In addition, rocket launches that go awry can result in debris raining down on populated areas or sensitive ecosystems, both of which occurred with the recent orbital test flights of the Starship. The history of space debris in Earth orbit can be traced back to the beginning of the space age in 1957. Like the history of spaceflight itself, it all began with the launch of Sputnik 1, the Soviet satellite, which officially inaugurated the space age and has led to decades of multiple launches and heavier payloads happening on a regular basis. In fact, close to 7,000 launches have happened since the Sputnik 1 mission, which excludes failed launch attempts, and the number of satellites these rockets have placed into Earth orbit numbers at around 21,000. Of these, roughly 14,050 are still in space, and around 11,200 are still functioning. Over time, this has led to a situation in Earth orbit where defunct satellites, spent rocket stages, and other debris will occasionally collide with each other, producing more debris. In addition, spent rocket stages and satellites often contain unused fuel. During an impact event, this will explode, causing debris to scatter even farther. In the history of spaceflight, more than 650 of these events have taken place, and according to the most recent numbers released by the Space Debris Office at the European Space Operations Center, roughly 40,000 of these space objects are regularly tracked by space surveillance networks around the world and maintained in a catalog. However, not all objects in orbit are large enough to track. According to the Space Debris Office, there are currently more than 40,500 space debris objects in orbit that are greater than 10 centimeters in diameter, or roughly 3 inches. For objects measuring about 1 centimeter, or 1/3 of an inch, to 10 centimeters, the numbers get significantly higher, at 1.1 million objects estimated. The Space Debris Office estimates that 130 million space debris objects are also in orbit, measuring between 1 millimeter and 1 centimeter. These objects pose a significant threat to operational satellites, spacecraft, and space stations, both current and future. While the majority of these objects may sound non-threatening, even the tiniest can pose a severe collision hazard. In low Earth orbit, objects are accelerated to the speeds as high as 7 or 8 kilometers per second, which works out to 12,875 kilometers per hour, or 8,000 miles per hour, when they impact a functioning satellite or other piece of infrastructure. At speeds like this, even the tiniest bits of space debris can cause serious damage to satellites, spacecraft, or anything else they happen to impact. However, the greatest danger that all this debris poses is the way it makes collisions more likely over time. This effect was described by NASA scientist Donald J. Kessler in 1978. As he described it, the density of objects in low Earth orbit would eventually become high enough that collisions between objects would cause a cascading effect, where objects collide, producing smaller objects which then collide with others, and so on in a vicious circle. This has come to be known as the Kessler effect, or Kessler syndrome. This effect was illustrated in the 2013 thriller Gravity, in which a Russian anti-satellite missile creates a high-velocity debris cloud that eventually triggers a massive cascading effect in orbit, leading to the destruction of the International Space Station, the Chinese Tiangong-1 space station, and forces all surviving astronauts in orbit to hastily return to Earth. The question then is, what can we do to mitigate all this orbital debris, and how can we prevent it from playing havoc with future missions? In short, how do we avert Kessler syndrome? Even though many scientists have argued in recent years, including Kessler himself, that we've already reached a critical point of saturation in low Earth orbit. The first and most important strategy, which space agencies and other organizations are currently doing, is to track objects in orbit and issue warnings about possible collisions in advance. That way, operational missions can adjust their orbit to get out of an object's path before it causes any damage. There are multiple entities that are dedicated to keeping track of the most hazardous objects in orbit. For NASA, this is done through their Orbital Debris Program Office, which monitors space junk using ground-based radar and optical measurements performed by other space surveillance systems. Russia and Roscosmos currently rely on similar methods, as does the European Space Agency. These efforts were formally organized beginning in 1982, where NASA held the first conference dedicated exclusively to space debris, which was followed by the European Space Agency holding the first workshop on the re-entry of space debris that same year. These events were motivated by two major incidents. The first happened in 1979 when Skylab, NASA's first space station, re-entered Earth's atmosphere and did not completely burn up, and ended with debris raining down on the surface. In 1982, there was also the breakup of the Soviet spy satellite, Cosmos 1402, which very nearly resulted in radioactive debris hitting the surface. By 1993, concerns about space debris led to the Interagency Space Debris Coordination Committee, which included representatives from NASA, the European Space Agency, the Japan Aerospace Agency, or JAXA, and the Russian Space Agency Roscosmos. This committee was created as a forum for multilateral exchange of technical knowledge and to allow members to coordinate on matters pertaining to space debris. Since its inception, several more agencies have joined, including additional European space agencies, as well as the China National Space Agency, the Canadian Space Agency, the Korea Aerospace Research Institute, the India Space Research Organization, and the State Space Agency of Ukraine. This reflected the growth and expansion of national space agencies around the world, as well as an easing of Cold War tensions, which came after the fall of the Soviet Union in 1991. In addition, the United Nations has kept an eye on space debris through their Office of Outer Space Affairs, or UNOOSA. Specifically, their Committee on the Peaceful Uses of Outer Space has held annual meetings where representatives of all UN member states come together to exchange research and information regarding their debris research activities. In 2002, the IADC published the IADC Space Debris Mitigation Guidelines, and presented them to the Committee on the Peaceful Uses of Outer Space, to the Scientific and Technical Subcommittee, which has since served as a baseline for national legislation and standards. Similarly, UNUSA has maintained the United Nations Register of Objects Launched into Outer Space since 1962. This database indicates which member states of the UN bear responsibility and liability for specific space objects. The UN also enacted in 1976 the Convention on Registration of Objects Launched into Outer Space. All member states and international organizations that agree to abide by the convention are required to provide information in the UN Register and establish their own national registries as well. Lastly, the UN General Assembly endorsed the Space Debris Mitigation Guidelines in 2007, which calls for member states to voluntarily adopt standards and measures to address the debris that result from their space missions. Nevertheless, the growth and expansion of the public space sector, as well as the commercial space sector, has accelerated the problems of space junk and indicated the need for more research and mitigation strategies. Even before the fall of the Soviet Union, launching satellites and other payloads into space was no longer the sole province of the world's two superpowers. Today, China, India, the European Union, and several smaller powers are also contributing, with more on the way. This includes, but is not limited to, the South African Space Agency, the Israeli Space Agency, the United Arab Emirates and its space program, as well as Iran and North Korea. But by far, the greatest contributor to objects in low Earth orbit has been the commercial space sector, otherwise known as New Space. Today, more and more companies are providing commercial launch services for telecommunication satellites, broadband internet satellites, as well as smallsats, otherwise known as CubeSats, where all the equipment necessary to power a satellite can fit within a much smaller volume. With the decline in launch costs, as well as the demand for services like satellite-based broadband internet increasing, the situation in orbit is only likely to get worse. In terms of the commercial satellite market, SpaceX has been a leading innovator. In 2015, Elon Musk announced the creation of Starlink, the purpose of which was to create a constellation of satellites in orbit that would be replenished regularly, capable of providing broadband internet access to all parts of the world, including remote regions and developing countries. The first batch of these satellites was launched in May of 2019, which consisted of 60 Starlink satellites deployed to a very low orbit of between 328 and 580 kilometers, or 200 to 360 miles. At the time, Musk stated that this decision was motivated in part to minimize the risk posed by space debris, and also because it would allow SpaceX to deploy more satellites sooner. Since then, SpaceX has received approval by the FCC and the International Telecommunications Union for constellations of 12,000 and 30,000 satellites respectively. This low deployment altitude also means that the Starlink satellites will see a more rapid decay in their orbits, requiring that more launches take place to replenish them. As of February 27, 2025, Starlink is reportedly the largest satellite constellation in orbit, with over 6,500 satellites currently in operation. Similarly, you have Project Kuiper, a subsidiary of Amazon established in 2019 by Jeff Bezos. On July 30, 2020, the FCC granted Amazon approval to deploy a constellation numbering 3,236 into low Earth orbit. So far, Amazon has not launched any of these satellites, with their main provider, Blue Origin, also owned by Jeff Bezos. However, launches are expected to happen soon, thanks to the completion of the New Glenn rocket, Blue Origin's heavy lift rocket capable of deploying satellites and other payloads to low Earth orbit. Under the FCC license, Amazon is required to launch and operate half of its satellites by July 30th, 2026, with the first constellation completed by 2029. The European Union is also looking to establish its own constellation, known as the Infrastructure for Resilience, Interconnectivity, and Security by Satellite, or IRIS-2. According to the latest updates, This constellation is scheduled to be deployed by 2027. Other commercial providers include Telesat, with its proposed Lightspeed constellation, Globalstar, and Iridium. Another contributing factor is the development of small satellites known as CubeSats. They are so named because of their shape and profile, 100 square centimeters or 15 square inches, which allows them to be stacked together to form larger scientific payloads. Also known as nanosatellites. The development of reusable rockets and rideshare programs has made them relatively cheap to deploy to low Earth orbit, where they're able to perform scientific studies for research institutes and universities, and greatly increase access to space research, which traditionally has been restricted to federally funded space agencies or large commercial satellite operators. While this has meant increased access to space and growing opportunities for scientific research, it also means that tens of thousands of additional satellites could be sent to orbit in the coming years. Further improvements in satellite technology and miniaturization have also led to a new class of picosatellites, or picosats. This refers to satellites with a mass that is typically below 1 kilogram, or 2.2 pounds. In terms of solutions, there are many possibilities, with mitigation and active debris removal, or ADR programs, being researched and tested. On the one hand, you have advocates for a no new launches policy, which would involve a complete halt to commercial launches and other non-scientific payloads or anything deemed essential for navigation, national security, or climate monitoring. However, a study conducted in 2005 by the NASA Orbital Debris Program Office found that even if no future launches occurred, collisions between existing objects would still trigger a cascade effect. This essentially means that, left on its own, the situation in low Earth orbit will continue to evolve, with more debris being created than is removed by atmospheric drag. As a result, nothing short of active debris removal will do. There are several ways to go about doing this, which include curtailing the creation of new debris, designing satellites to withstand impacts, and adopting procedures to reduce the risk of collisions and breakups. For example, in order to reduce the risk of explosions in orbit caused by unspent rocket fuel and chemical propellants used by maneuvering thrusters, a method known as upper stage passivation has been proposed. In this scenario, spent stages and satellites will release any residual propellant they still have in order to reduce the risk of explosions caused by collisions. There's also the one-up, one-down policy, where space agencies and commercial providers would be responsible for removing an object and deorbiting it for every new payload they deploy. Yet another method is to deploy satellites so that they will enter Earth's atmosphere and burn up sooner. Both OneWeb and SpaceX adopted this policy in 2017. By placing their satellites in very low Earth orbit, they are likely to burn up in the atmosphere 1 year after deployment. Other methods address the mission architectures themselves. As Dr. Mariba Jah indicated in a previous episode, satellites and spent rocket stages are treated the same way single-use plastics are, in the sense that they are designed to only be used once, and then discarded. While the development of reusable rockets have made first-stage boosters retrievable, second-stage boosters are still expendable. As a result, a strategy has been suggested where second-stage boosters could be launched to ensure that they reach an elliptical geocentric orbit that will allow for rapid orbital decay followed by a burn-up in Earth's atmosphere. However, there are currently no international treaties that make these measures legally binding. While international frameworks exist, such as the guidelines produced by the Committee on the Peaceful Uses of Outer Space in 2007, laws regarding launches are a matter of national law and national responsibility. In this vein, it has been suggested that governments could incentivize commercial space companies to clean up space debris. This could take the form of grants to develop the necessary technologies for debris removal or penalties for pollution. But perhaps the most promising strategies involve autonomous spacecraft that are capable of rendezvousing with debris objects and forcibly deorbiting them, burning up both in the process. Multiple concepts have been explored by NASA, the European Space Agency, and others. Examples include drag sails, which NASA partnered with Vestigo Aerospace to conduct a 6-month study to assess their feasibility. These drag sails, when attached to orbital debris, increase atmospheric drag, forcing the objects to enter Earth's atmosphere sooner. The European Commission also spearheaded a project known as Horizon 2020, Future and Emergent Technologies, which has fostered ideas for dealing with space debris, including a tether system that could be attached to satellites and deployed once the satellites become defunct, so that they are capable of deorbiting themselves. Such a system was developed by researchers from the Universidad Carlos III de Madrid and is known as the Electrodynamic Tether Technology for Passive Consumable-less Deorbit Kit, or ETPAT, which is essentially a strip of aluminum tape that is coated with special material that causes the tether to become attracted to Earth's magnetic field. You also have the Remove Debris spacecraft, developed by Surrey Satellite Technology and the Surrey Space Center and Airbus Defence. This small satellite was sent to the ISS as part of a study to evaluate its effectiveness at removing debris by relying on a harpoon, a tether, and a drag cell. The European Space Agency has also proposed magnetic space tugs, satellites that would generate magnetic fields to both attract or repel space debris and force them into decaying orbits. There's also been significant research in directed energy methods. In this scenario, special satellites equipped with lasers would be launched that would use these lasers to push orbiting debris into the atmosphere or to incinerate it in space. So far, NASA and the China National Space Agency have conducted feasibility studies in this area. Alas, the best strategy, and currently the only one we have, is to actively monitor space debris and provide alerts about possible collisions. This allows operators to adjust the orbits of their satellites and is routinely done aboard the ISS, which periodically needs to adjust its orbit in order to reduce atmospheric drag. However, the ISS's engines, or those of any spacecraft mated to the station, can and are also used to raise and lower the station's orbit so that it'll avoid the orbital path of debris or defunct missions. Shielding is also employed in order to ensure that objects that are too small to be tracked will not cause significant damage to the hull. And while all proposed methods for active debris removal are either in the research and development phase at this point, and are likely to be rather expensive to implement, there's no question about their necessity. Already the situation in orbit is untenable, unsustainable, and will require active cleanup in the near future. This is necessary not only to ensure that satellites can operate safely in space, but that commercial space stations and other proposed successors to the ISS, which is due to be decommissioned in 2030, will not be threatened. Similarly, the future of space tourism, as well as all missions that would take humanity to low Earth orbit and beyond, require that orbital debris be brought under control in the not-too-distant future. Given the commercialization of low Earth orbit and humanity's growing presence in space, it is possible to envision a future where the space lanes are actively monitored and regulated in the same way that airspace here on Earth is. What is also required is a fundamental shift in our thinking. As humanity's presence in space grows, it is becoming increasingly obvious that our perceptions of space need to evolve. Far from it being a big, vast, and empty space that we can simply throw our garbage into, which includes our launch vehicles that we use to send payloads and people to space, space and Earth are part of the same collective heritage that we intend to pass down to future generations. Long-term plans and long-term strategies are therefore necessary to ensure that future generations are not forced to deal with the consequences of our current and wasteful behavior. Tune in again soon when we'll be talking about the James Webb Space Telescope, its most recent rounds of discoveries, and the naming controversy which, despite the passage of time, is still relevant. We'll also be looking at the future of NASA, which finds itself in a bit of an existential crisis thanks to the latest administration and the deep cuts it's proposed to NASA's budget. In the meantime, thank you for listening. I'm Matt Williams, and this has been Stories from Space.
hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.